In the last video where we launched something at an angle, we figured out the horizontal and the vertical components of that launch velocity. And we use the vertical component to figure out how long that thing is in the air. And then we use that time to figure out how far it'll travel given a constant horizontal velocity. What I want to do in this video is to redo part of that problem. And I want to redo the part to figure out how long this object stays in the air. And I'm going to do it in a slightly more complicated way than the way I did in the last video, but it's kind of a more powerful way, and we'll see that it's more powerful in future videos. So in the last video, to figure out how long it's in the air, we said, look, we're starting and stopping at the same elevation. Whatever our vertical velocity is here upward, we're going to have the same magnitude of velocity, but it's going to be downward. We use that insight to figure out the change in velocity, and then we use that change in velocity and the constant acceleration due to the force of gravity on an object in free fall to figure out the time in the air. And it was pretty simple mathematically. What we're going to do now is to derive a formula that's useful in physics, although I like to always derive it from scratch, and that's why we're going to derive it over here. And you've seen me derive this formula before. But just to start off, we need to remind ourselves that the vertical velocity that we calculated in the last video was 5 meters per second. And given that vertical velocity, let's figure out how long this thing stays in the air. So our vertical velocity, our velocity in the y direction is 5 meters per second. And also as a reminder, our convention when we're dealing with vectors in one dimension, and this is essentially in one dimension now, since we know it's in the y direction, is positive means up, negative means down when we're dealing with the vertical direction. When we're dealing with the horizontal direction, positive means to the right, negative means to the left. So just to make sure we have those conventions down. So how can we figure out how long this thing stays in the air? So we can remind ourselves that the displacement, and everything we're talking about now is, well, this will actually apply whether in any one dimension, but the displacement is equal to the average velocity, the average velocity times our change in time, times the amount of time that elapsed. And what is our average velocity? Our average velocity is our, if we assume constant acceleration, it is our final velocity. It is our final velocity plus our initial velocity. Actually, let me write it this way. It'll make it a little bit cleaner. It is our initial velocity plus our final velocity divided by 2. So literally the arithmetic mean of our initial and final velocities. And we're going to multiply that times change in time. Times change in time. Now what is our final velocity going to be? Our final velocity, I'll write it over here. Our final velocity, your final velocity is the same thing as your initial velocity. It's the same thing as your initial velocity plus acceleration times your acceleration times how much time has passed by. This right here is your final. This right here is your final velocity. So let's substitute that back into this right over here. And what do we get? We get our initial velocity. So our average velocity is now our initial velocity plus our final velocity. The final velocity is this over here. So it's our initial velocity plus the acceleration times the amount of time that passes by. All of that divided by, let me do that same color, all of that divided by 2. All of that divided by 2. And all of this is multiplied by the amount of time that passes by. Once again, this is our total displacement. So this part right over here, get it in magenta, we have 2 VIs. Right? So that simplifies to 2 VIs, 2 times our initial velocities. And so this expression right here simplifies to 2 times VI divided by 2 is our initial velocity. And then we have, well, I'll just do it all here, and then I'll multiply times the time elapsed after that, plus the acceleration times time, the acceleration times the amount of time that's passed by, divided by 2. And all of this is multiplied by the amount of time that passes by. And this is our total displacement. And we're almost done. And if you have to take a physics exam under time pressure, it's not ridiculous to not have to rederive it every time. But I want to emphasize that you should realize that these formulas come from almost just common basic sense principles. and you should be able to derive them. But it's good to memorize them if you have a time pressure exam. So now if we multiply this delta t, you get the total displacement is equal to your initial velocity times your change in time, plus, I'll do it in the same color, plus your acceleration over 2 times, you have a delta t times a delta t. Remember, delta just means change in time. This triangle just means change in time. So change in time times change in time is change in time squared. Change in time squared. And this expression right here, this is in some physics books or in some classes, they'll just give you this formula. But I wanted to just show you that it's derived from very, very simple principles, from just displacement is average velocity times time. What is average velocity? What is final velocity? It's just initial velocity plus acceleration times time. And you'll get this expression right over here. So I did this to figure out how much time we're going to spend in the air. So how do we do that for this particular problem? Well, we know our initial velocity. That's the vertical component, because we're dealing with just the vertical component here. We know our initial velocity. We know the acceleration due to gravity. And in this situation, we want to figure out when the displacement is going to be, and this is going to be a little bit unintuitive, but hopefully it makes sense, when the displacement is going to be 0. Because there's going to be 2 times when the displacement is going to be 0. There's going to be the time right when we launch it, right at time 0, the displacement is going to be 0. Then this thing's going to be launched and then come back to the ground. And then when it comes back to the ground, the displacement is going to be at 0 again. So if we set the displacement to be equal to 0, we should get 2 answers to that. And one of them should have a non-zero time component. One of them will probably be 0, and the other one will have a non-zero time. And that's the one that we should go for, because that's the second time. That's the time when we've hit the ground. So let's apply that. So we have the displacement is going to be 0. So 0 is equal to our initial velocity is 5 meters per second upwards. I won't write the units just for the sake of space. 5 meters per second upwards times change in time, plus, what's our acceleration? Well, our convention is if something's going downwards, if the one-dimensional vector is going downwards, it's negative. So the acceleration is negative 9.8 meters per second squared. You divide that by 2. So we get, actually, let me just write it all out. Actually, let me write it like this. It's negative 9.8 meters per second squared. I'm not writing the units here just for simplicity, just so that we don't take up too much space, times, and then all of this times delta t squared. And lucky for us, this one is pretty simple. We don't have to resort to factoring, or we will factor, but we don't have to resort to the quadratic formula or anything like that to solve this quadratic equation. Right over here, we can factor out a delta t. So we get 0 is equal to delta t times 5 minus 9.8 over 4.2 is 4.9. 4.9, and if you factor out a delta t out of delta t squared, you're left with another delta t. So there's 2 solutions here. There's 2 ways to get, there's 2 delta t's that'll give us 0. Either this delta t is equal to 0, so either delta t is equal to 0. That's just our starting point, so that's not the time that we're interested in, when no time has passed by. Or all of this business could be equal to 0. If we have 2 things, when they take their product and equal 0, that means either one or both of them are equal to 0. So we have 5 minus 4.9 delta t, 4.9 delta t is equal to 0. We could add 4.9 delta t to both sides of this equation, and we will get 5 is equal to 4.9 delta t, 4.9 delta t, and then we divide both sides by 4.9. We divide both sides by 4.9 to get the elapsed time. So delta t is equal to 5 divided by 4.9 is, we're at the home stretch, 5 divided by 4.9 is equal to 1.02 seconds. So it's equal to 1.02 seconds. And so once again, we got the same exact answer we got in the last one. We just used a different method. And that's one of the really fun things about physics, is as long as you're doing logically consistent, correct things, there's many ways to often get that answer, but it should be the same answer. If it's not, you probably did something wrong in one of those 2 ways of doing it.